Okay, so we're going to run through some what I'm calling slightly more advanced rational exponent problems. These are problems where we're just taking what we know about rational expressions and looking at some algebra problems that are maybe look very complex, but once we recognize some key features, they'll simplify really quickly. So in this first problem here, again, when you take a look at this, I'm guessing when you see it, it looks fairly intimidating. There's a lot going on in this problem. But when we look at it at its smaller pieces, what I see is a couple of things. I see, for example, right here, just a fraction that says 8 over 4, which is not all that unreasonable. We know 8 over 4, right? And I see that I'm raising something to a 1/2 power. So let's just remember what a 1/2 power means. If I do something like x to the 1/2, what I really mean is that the denominator of my exponent is really an index number for the radical that's going to include my base. So these two things are equivalent, and if you remember, an index of 2 just really means square root. So if you notice what's happening here is that this problem is actually just the square root of 54x to the 5th. So I can rewrite this and I can simplify a couple of different ways. 8 over 4, I'm going to simplify that fraction into 2 over 1. And then I'm going to take the 54x to the 5th, and I'm going to recognize that these two numerator and denominator pieces are just different ways of writing the same thing. They're both asking you to take the square root of something. So I'm going to change the format of the first one so that it matches the second one, and it makes it a little bit easier to simplify them because now they're using the same notation. They're both using square root. Instead of one being an exponent and one being a radical, I'm saying, well, wait a second, they mean the same thing. Okay, so now for this problem, I'm going to recognize that we have a property here that lets me say that if the numerator and the denominator of a fraction have the same radical, that I could put that numerator and denominator underneath the same radical and say this is really 54x to the 5th over 3x to the 3rd, all under one radical. It's entirely okay. We have a property that says if the numerator and the denominator have the same radical, that I can put all that information under one big radical, and then this 2 over 1 just becomes a big multiply by 2 on the outside. Right? 2 over 1, remember, is just 2, and this is being multiplied. So this is now equivalent. Okay? And I did that because I recognize that 54 divided by 3 is something that works out really nicely. 54 divided by 3, it looks like it goes, 54 goes into, 3 goes into 5 just one time. Okay? And 3 goes into 24 8 times. Okay? And then I can also do the same thing with my variables. X to the 5th and x to the 3rd divide nicely into an x squared, and again that big 2 sitting out front being multiplied by this expression. Okay, and so now this is a very simple problem. We can just bring out the perfect square of 9 that's in 18. Okay, and I have a 2 left over, and I have this x squared, which is going to also square root. So here's my final answer. This says 2 times 3, which is 6. The square root of x squared I can do as well. That's just x, and the only thing here that I can't simplify is this square root of 2, so that's going to stay underneath the radical. Okay, so again, at the beginning it looks fairly intimidating, but the reason that it looked intimidating was because my numerator and my denominator were using two different versions of the same operation, which is just taking the square root. Right? So once we put things in equivalent form, we can use what we know about radicals and we can simplify this. Okay, so we can also take a look at problems where we ran into an issue before. So for example, in this problem, we got a rule that says you're allowed to multiply together radicals as long as they have the same index. And in this example, they don't have the same index. One has a 3 and one has a 5. And so what we can do to multiply these together and try to get some kind of simplified combined result is to turn them into their exponent form and see if maybe we can do something with it in that form. So remember, this means the same thing as x squared to the 1/3, right? That's my first expression. And the second one is the same thing. It's x to the 4th to the 1/5 power. And then I can simplify each of those and multiply together my exponents and say this is really x to the 2/3, right? And x to the 4/5. Okay? So I can simplify exponents when the bases are the same. And to do that, we're just going to add the exponent. So I'm just going to come off to the side here and figure out what 2/3 plus 4/5 is, so I don't have to rewrite my whole problem. Well, I need common denominators, and in this case, my common denominator is 15. Right? I'd like them both to have a 15. So I need to multiply the denominator by 5, which means I'll multiply the numerator by 5 as well, so that's 10. And then here I need to multiply both of them by, it looks like, 3. So I'd get 12. Okay, so if I simplify this, this looks like 22 over 15. Okay, so that means that I can simplify this expression by adding the exponents, and I get x to the 22 over 15. So since my original problem was in radical form, I'm going to turn this back into radical form. And remember, the denominator is my index, so this is the 15th root of x to the 22nd. Okay, and I'm pretty much done, but I can do a little bit more simplifying here, and that's because there are more exponents on the inside than there are index numbers on the outside. So watch what I do. I'm going to break up the 22 x's into 15 x's. Okay, and then I have 7 remaining x's left over. And I did that because at least these 15 will root. Okay, I can divide my exponent and my index and say that this is just x. Right, the 15th root of x to the 15th is just x. And then I have these extra ones that I can't do anything with. Right, so if I want to combine using multiplication radicals that have different index numbers, I can turn them into their exponent form, and then I can proceed like I would with exponents, and then if I want to convert them back, I can find some kind of expression that is a combined version of those two answers. Okay, so how you're going to use that's entirely up to you, but that's something that we can do if we should come across it. Okay, so if I take a look at something like this, it's the same kind of thing. I'm looking at these and I'm saying, okay, I'd like to put these together. I'm going to use my exponent rules first and say 2/4 becomes 1/2. Okay, and then I'm going to say 4/5. Well, there's a division symbol in between 4/5 and 2/3, and in my exponent rules say that I should subtract, not add, the exponents. So that's the only difference. Is the last example was multiplying. These ones are dividing, so I'm going to change my exponent operation from addition to subtraction. So very similar. Again, these are both 15ths. If I want to subtract fractions, right, this first one is 12. And my second one is, when I multiply the top and the bottom by 5, a 10. So this is really just 2/15. Okay, so I'm going to say that this is the same as x, so the 2 over 15. Right, and so I could leave it in this form. If I wanted to see the radical form of this, remember this would be the 15th root of x squared over 2, and that's actually simplified. I don't have to do anything more than that. There are less exponents than my index, which means I can't bring anything to the outside, and I would say that this is done. So these are actually equivalent forms. It's okay to leave either of them. It depends on which version is more useful to you, or if you're doing an exam problem, which version is presented to you. Okay, so a couple more advanced problems. We actually have one more. We'll take a look at this. What happens if I have a decimal? Okay, and that decimal is actually a negative exponent, right? So we have a couple things to worry about here. So let's start off with the first problem. That is that 1.2, when we talk about decimal and fraction exponents, we like the fraction form of them. So I'm going to say that 1.2 is the same as x to the negative 12 over 10. And I know that because this ends in my tenths place. I can simplify 12 tenths a little bit and say this is x to the negative 6/5. Right, I divide the top and the bottom by 2. And so now the question is, well, how do I simplify this? Okay, I know how to handle the 6/5. That's my index, and that's my the numerator. The 6 is going to be just a regular exponent, but I have this negative sign as well. So let's see what that does to things. Okay, if you remember, negative exponents mean take the reciprocal. So this is really 1 over x to the positive 6/5. Okay, so if I put this now in radical form, it's the 5th root, of x, to the 6th power. Okay, so we got to figure out now how to deal with this. All right, so I'm not allowed to have radicals in my denominator. Okay, so I'm going to bring this way back over here. We're going to need a little bit of space. Okay, and I'm going to say that this is the same thing as 1 over the 5th root of x to the 6th. Right? Well, I'd like to be able to 5th root the bottom of this fraction. I want the denominator to go away, so I want a nice multiple of 5 to be showing up in the exponent spot, which means I need to rationalize this. I need to multiply the numerator and the denominator by the 5th root of x to the 4th. And the reason I picked x to the 4th is because now when I multiply these together, I'm going to get a 10 in my denominator, and that's going to 5th root. Right? This is now the 5th root of x to the 10th, which is the 5th root of x to the 10th. If I simplify 10 divided by 5, exponent divided by index, I just get x squared. Okay, so I'm going to say in this case the fifth root of x to the 10th is x squared. Okay, but because I changed the denominator of this in order to rationalize it, I need to change the numerator as well. This is going to become the fifth root of x to the 4th up here. Okay, which means that's just going to kind of carry along throughout my problem and show up in my final answer. Right? And I would say this would be a radical version of x to the negative 1.2 in its most simple radical form.